This is a short clip from a larger video, which is also part of a three-part series that See the Pattern has done, or Gareth has done, about electrical stars and the electrical sun. This one was just talking about variable stars. Variable stars are stars that change their brightness over periods of time. Sometimes it's just they're stars that are going through a transition from like the main sequence to a red dwarf. And a lot of these there are many types of these, but this is not. These are about stars that have merged together that have created variable stars. So, let Gareth talk here for a few minutes.
In the standard model of star evolution, the stars age slowly and they move across the Hertzsprung diagram along the main sequence from top left to bottom right, taking millions of years to carry out this journey. During this process, they use up their nuclear fuel and undergo changes due to the change in composition and the change in terms of what they're actually burning in the core. Eventually, either dying in a supernova explosion or running out of fuel altogether and simply cooling over a very long period of time. At the extremes of the main sequence, we have the red giants, and these are stars which are cool but luminous, so they are extremely large, and their diameters can actually change by up to 60% over a given period of time. And their density is extremely low, about 1/10,000th the Earth atmosphere, and some astronomers have actually described them as red-hot vacuums. Some have extremely low surface temperatures, lower than about 1,000 degrees Kelvin. So the question is, how do these stars with such low densities and surface temperatures possibly maintain nuclear fusion? Now, in an electrical model, these stars are simply experiencing very low excitation. And in the lower left, we have the white dwarfs. They have very low luminosities but are extremely hot. In the electric star model, they are explained as having very high current densities. In the standard model, these stars are described as being at the end of their life, having expended all of their nuclear fuel billions of years previously, and they are left to cool very, very slowly, like cooling embers on a fire. The light they emit comes from the heat remaining from the earlier nuclear fusion. Now, our Sun is about 4.5 billion years old, and it's not even halfway through its life cycle. And the problem is that no one has actually observed this process, and our records for the stars only go back a few thousand years at best. So there are some really good examples that show that this slow evolution of stars is wrong, and that actually what happens can be very dramatic and very rapid. So let's examine some of those examples. FG Sagittae. Now, this star has changed from being a blue star to a yellow star since the early 1900s, and recently its luminosity has dropped significantly. In the early 1900s, FG Sagittae was a hot star about 50,000 Kelvin and had a magnitude of 13. And over the next 60 years it cooled to about 8,000 degrees Kelvin, and the brightness changed to a magnitude 9, so it increased its brightness, and it shifted its radiation from ultraviolet to visible light. Now, in the 1970s, new spectral lines appeared for strontium, yttrium, zirconium and barium, and from the 1970s to the 1980s the temperature continued to drop. In 1992 its magnitude suddenly dropped to 14, and this continued through to 1996, when its magnitude had dropped so much that a companion star became visible. Was this caused by electrical fissioning, the sudden nova-like brightness increase followed by a rapid decrease in luminosity, a loss of temperature, the discovery of a new companion, and the fact that it sits within a nebulous nova remnant? Aquila and Sagittaria are objects that have been observed since the 1920s and show very similar traits to what we've just discussed. Both have changed their spectral type and their surface composition very rapidly. Monocerotis. Over a 2-week period in January 2002, an astronomer observed a new star appearing. and over the next few months it brightened to a magnitude 6.5 and then faded again, and it was surrounded by a glowing cloud, and the cloud has expanded over time. And then currently it is only a magnitude 16 star, and for a short period of time it was one of our brightest stars in our own galaxy. It is also a binary pair, and it is the coolest supergiant that we have ever observed. In March 2002 it was around 4000 Kelvin, just 7.
Okay. FG Sagittae and V605 Aquilae and V434 Sagittaria are probably what they call our Corona Borealis variables. These are white dwarfs that have merged together over time. The reasoning they think that this is the case is because the stars are very low in hydrogen and high in stuff like carbon, and which indicates it was in its white dwarf phase. And what's happened is when they merged, they started burning helium temporarily in a thin shell in its outer core, and eventually the soot from the helium fusion into carbon, and the carbon in the white dwarf phase star prevented more fusion from happening, and the star cooled off and expanded out to like a red dwarf, and the red giant, and the red giant the phase keeps expanding over time. The V838 Monoceros, there's suspected to be two binary stars that emerged again, and over time, and became one star. It happened. A lot of these stars are fairly close together, and they cause like a gravitational drag on each other, and they'll become one star. So it still has to be figured out the fine details, but this is what scientists have come up with so far about these two. Okay, there's more to electrical star formation, as he's alluded to, as planets coming out of stars and stars splitting off because there's too much electrical stress, which nobody's detected any currents, I don't think, in space, so we don't know where they get that from. But it's probably going to be a few videos long, just to be subdivided into different topics. But hopefully somebody found this interesting or educational, and have a good day. Bye.